I am Dr. Neeraj Upadhyay, an assistant professor in Department of Chemistry, Dr. Hari Singh Gaur, Vishwavidyalaya Sagar. In the last lecture, we introduced lanthanoid and actinoid series. The lecture we started with the definition of lanthanoids and actinoids. They are called inner transition element because filling of electron in nf orbital start after filling of electron in n plus 1d orbital. So, they are the part of transition series, but since the last electron fill in the inner shell of it, therefore, this type of series is called inner transition series. Properties of 4f elements resembles with the properties of lanthanum. It is therefore, the series is called lanthanoids. Similarly, elements of 5f series are called actinoids because the properties resembles with actinium there. Since the new electrons in these series enter into inner penultimate shell, it is therefore physical and chemical properties of these elements are almost same. They all are metals. Their density increases when we go left to right in a period. They all are highly electropositive and react easily with electronegative elements like oxygen and fluorine. All lanthanoids have +3 oxidation state common except europium and ytterbium. The most stable oxidation state of europium and ytterbium is +2, whereas in case of cerium, the stable oxidation state is +4. The maximum oxidation state in lanthanoids can reach up to +4 only. But in case of actinoids, the highest oxidation state is +7. They form coordination compounds, and due to their larger size, the coordination number may reach to 8 to 9. But ligand field has low effect on f orbital as they are in the inner penultimate shell. It is therefore, the stability of such compounds are low and ligand exchanges are very common. In this lecture, we will deal with other properties of lanthanoids and actinoids, especially with color and magnetic properties of these compounds. Also, we will learn about lanthanoid contraction, which is highly important especially when we talk about periodic properties and separation of lanthanoids. After learning this lecture, you shall be able to know about color of lanthanoids and actinoids and mechanistic background behind that. You will be able to analyze magnetic behavior of lanthanoids and actinoids and concept behind that. You will also be able to know the cause of lanthanoid contraction and their consequences. Most of the lanthanoids in its metallic form are silvery white, but in their trivalent state, mostly they are colored. They can produce color in its +3 or in higher oxidation state, both in crystalline as well as in solution form. The energy of absorption increases with increase in the number of unpaired electrons in the f orbital. F orbital contains a maximum of 14 electrons. It is observed that the color of lanthanoids in its +3 oxidation state that contain x electron in its f orbital show similar color as that of its counterpart of 14 minus x electron in the f orbital. It means color depends on number of unpaired electrons in f orbital. You can see the observed color in the table which is shown on your screen. Elements that contain 0, 7 or 14 electrons in the f orbitals are colorless. This is because they cannot have any FF transition. So, these observations indicate that the origin of color is in FF type of transition. As we can see, the metallic lanthanoids are silvery white, but in the ionized state, most of them are colored. This is because in the +3 oxidation state, ligand field can affect directly the f orbital, and therefore, splitting of f orbital is more effectively done. Also, during FF transition, system follow spin selection rule, and therefore, ion containing unfilled, half-filled or fully filled orbitals are colorless. In the electronic spectra of the compound of these elements, most of the FF transition give sharp peak, that is, their peak in the electronic spectra is very narrow like a line. This sharpness is due to fact that f orbitals are well screened from the ligand field by 5d and 6s orbitals. Also, the intensity of color of such elements are very weak as they are Laporte forbidden. However, Laporte allowed transitions are observed in some of the compounds of cerium 3+, terbium 3+, samarium 3+, europium 2+, and ytterbium 2+. The Laporte allowed transition is done as 4Fn to 5D1. Actinides ions are usually colored, but in some cases they show variable color that can vary compound to compound. Here also, ions having F0, F7 and F14 configuration are colorless. So, it is clear that color is due to FF transition. Ions having 7 or more electrons in the 5F sublabel show sharp peak and give resemblance to lanthanoids. But ions less than 7 electrons in F subcell give comparatively broader peak and therefore show less resemblance with lanthanoids. So, please look on the screen, see the table of the color with variable oxidation states. The color arose in actinides are due to FF transition, FD transition or from the charge transfer. Since 5F are more exposed than 4F electrons, hence they are influenced by the ligands and have around 10 times stronger than FF transition and 2 times broader absorption spectra than lanthanoid ions. As we learned in our module number 14, any charged particle, if completing a loop, generate magnetic field. Electron can complete such loop by 2 different ways, either by spinning on its own axis or through orbital motion. Thus, we got to know there that the spin magnetic moment of unpaired electron may couple together to produce spin only magnetic moment with the formula mu s is equal to root under 4s into s plus 1 Bohr magneton. Similarly, the magnetic moment of orbital angular momentum, if not quenched, may also affect the overall value of magnetic moment. The magnetic moments in such cases were calculated by counting both the spin and angular momentum contribution, but separately. Hence, the value of magnetic moment would be determined by the formula mu s plus L should be equal to root under 4s into s plus 1 plus L into L plus 1 Bohr magneton. In transition metals, especially in 3D series, the contribution is usually quenched out by interaction with the electric field of the ligand in its environment. Thus, as a first approximation, the magnetic moment can be calculated using the simple spin formula, that is mu s should be equal to root under 4s into s plus 1 Bohr magneton. When we calculate this in terms of number of unpaired electron, mu s becomes root under n into n plus 2 Bohr magneton. Here n is number of unpaired electron and mu is the magnetic moment. Now, the 4f orbitals are well shielded by 5s and 5p orbitals. It is therefore the electric field of the ligand do not quench the magnetization generated due to angular momentum of the electron. So, both spin and angular momentum contribute to the overall magnetic moment of atom or ion. The quenching of orbital angular momentum in second and third transition series is also not done, but the magnetic properties of lanthanoids are fundamentally different from those of the transition elements. Before this point, we learnt about SS coupling, LL coupling, but in case of lanthanoids, spin and angular momentum couple together. When spin and total angular momentum couple together, they generate a new kind of quantum number called spin angular momentum quantum number, and this is represented by J. If f orbitals are less than half filled, value of J becomes L minus s, while if f orbitals are more than half filled, the value of J becomes L plus s in their ground state. The magnetic moment mu is calculated in Bohr magneton by the formula mu J is equal to G root J into J plus 1, where G is a gyromagnetic constant and its value can be determined by the formula G is equal to 1 plus S into S plus 1 plus J into J plus 1 minus L into L plus 1 divided by 2J into J plus 1. Here S is the total spin contribution, L is total angular momentum contribution, and J is L minus S when the shell is less than half filled, and J is more L plus S when the shell is more than half filled. Elements containing 0 or 14 electrons in its F subshell are diamagnetic. Thus, lanthanum ion La3 plus and cerium ion Ce4 plus and lutetium ion Lu3 plus are diamagnetic. All the other elements contain at least one unpaired electron and therefore they all are paramagnetic. The paramagnetic behavior increases with increase in number of unpaired electrons in F subshell. Magnetic moment of actinoids are less compared to the theoretical predicted value of magnetic moment. This is because the 5f electrons are nearer to ligand field and therefore they are less shielded compared to 4f orbitals. So, very little quenching of orbital angular momentum in 5f orbitals are observed. Generally, when we go down the group, radii increases. Similarly, ionization energy, electron affinity, electronegativity decreases because of increase in the energy level. This statement you are reading from long back, that is from your intermediate classes. But you know the change in radii of elements between second and third transition series is very small, especially after entry of 14 members of lanthanoid series. For example, metallic radii of the first element of first, second and third transition series increases when we go down the group. That is, metallic radii of scandium is smaller than yttrium, the size of which is lower than that of lanthanum. So, no issue. This is in accordance with our learning of previous classes. But when we see the metallic radii of titanium, zirconium and hafnium, the order of metallic radii changes. It means metallic radii of size of hafnium, which is an element of third transition series, becomes smaller than the elements of the same group of second transition series. The periodic trend or the periodic properties also revert and become static when we compare with the second transition series. This loss of trend in periodic properties when we go down the group especially come after filling of lanthanide series. So, why this anomaly come? All you know, f orbitals are far away from the nucleus. The penetration of f orbital towards nucleus is smallest among the orbitals, all we know, that is sp and d orbitals. Since these orbitals are not very attached to the nucleus, it is therefore f orbitals are very diffused. When we go left to right in lanthanide series, number of protons increases and therefore the valence electrons are getting more attracted towards nucleus. At the same time, an electron in inner penultimate level, that is in 4f subshell, also increases, which is expected to screen some of imaginary lines of forces that originate from nucleus and fall onto the valence electron. Unfortunately, f orbitals are very diffused and therefore only a small fraction of such lines of forces are screened by the electrons of f orbitals. It is therefore size of lanthanoids decreases when we go left to right in a period. Such steady decrease in the size of lanthanoids and their ions with increase in atomic number is called lanthanoid contraction. The overall decrease in atomic and ionic radii from lanthanum to lutetium is called the lanthanoid contraction. This is an unique feature in the chemistry of the lanthanoids. The effect of physico-chemical properties of post-lanthanoid elements due to lanthanoid contraction sometimes is path changing. It is due to the net result of lanthanoid contraction that the elements of the same group of second and third D series exhibit similar radii. For example, zirconium has atomic radii 160 picometer. Hafnium, which comes below this zirconium element, has atomic radii 159 picometer, that is lesser than the size of zirconium. But the size is very close, and therefore they have similar physical and chemical properties, which is much more than that we expect for usual family relationship. The ionization potential and electron affinity is expected to decrease when we go down the group, but post-lanthanoid elements of same group do not follow this trend. Inert pair effect becomes sound after lanthanide series. For example, both tin and lead show inert pair effect, but tin shows both the oxidation state +2 and +4, while lead show only one oxidation state, that is +2 in its stable configuration. Due to lanthanoid contraction, almost all types of radii of these elements decreases when we go left to right in the same period. Also, the size of elements of second and third transition series are very close. Separation of lanthanoids. Lanthanoids have similar sizes and almost similar physico-chemical properties. Also, they are found in nature in combination with each other. It is therefore difficult to separate them. Basic strength of hydroxide. Due to lanthanoid contraction, size of M3 plus ion decreases. According to Fijan's rule, we know that decrease in size of cation leads to increase in the covalent character of it. Due to increase in the covalent character in MOH bond, their basic character decreases. So, hydroxide of La3 plus is most basic and of Lu3 plus is the least basic. Similarity of second and third transition series. The atomic radii of second row transition elements are almost similar to those of the third row transition elements because of the increase in size on moving down the group from second to third transition series elements is cancelled by decrease in size due to lanthanoid contraction. Since trends in periodic properties are very affected by radii of elements, especially when we are going down the group. So, because of similarity in size of second and third transition series, they are similar to each other. Their periodic properties are similar to each other. The elements of 4F series are silvery white, but in its ionized state they show different colors in their crystalline state as well as in their solution form. The lanthanides ion having configuration other than F0, F7 and F14 can produce color. Most of the compounds with F7 configuration do not show any color. Also, the color of Fn and F14-N ionic configuration are almost same. This indicates that the main electronic transition is FF transition. The intensity of such colors are low as they are Laporte forbidden. The absorption spectra of lanthanoids are sharp, which is not broad as that of the spectra of transition elements. The ions of the elements containing less than 7 electron in their F subshell show very sharp peak, but with increase in the electrons than this number, the broadness in peak increases. Also, the peak of electronic spectra of actinoids are broadened than the corresponding lanthanide ions. Since lanthanoids and actinoids are far away from the ligand field, the angular momentum of f electrons are not easily quenched. Also, the magnetic field generated due to spin and angular momentum of such elements get coupled together, and new magnetic moment depends on a new quantum number called total spin angular momentum quantum number. They are calculated by using the formula mu j equal to g root j into j plus 1 Bohr magneton. Most of the lanthanoids are paramagnetic, while lanthanum 3 plus, lutetium 3 plus, ytterbium 2 plus and cerium 4 plus are diamagnetic. Similarly, most of the actinoid ions are paramagnetic because they contain unpaired electrons, while the ions which have electronic configuration F0 and F14 are diamagnetic. The f orbitals are highly diffused and therefore show very low shielding. It is therefore radii of elements of lanthanoid series decreases as we go left to right in a period. This decrease is that much sharp that after filling of these 14 electrons in F subcell, the periodic properties of elements of 4d and 5d series becomes almost identical. Similarly, the size of lanthanoid become very close to each other, and therefore their physico-chemical properties also become identical. Lanthanoids in their ore exist in combination. Because of similar properties of lanthanoids, these are difficult to separate. In our next module, we will learn about the method of separation of lanthanoids. Thank you very much for listening this lecture carefully. Thank you.